Now we will apply Ampere's law to find the magnetic field inside an ideal solenoid. Of course, everybody knows what a solenoid is. You know, these are the coils, and probably this is the most common type of an electromagnet. It's used widely in all types of motors and other applications where an electromagnet is needed. So it's a coil where you have, you know, and you have the wire wound to form like a long coil, and it's characterized usually by a number of turns per unit length. Okay. Now, of course, a solenoid has a finite length, but what we are going to do here is, as usual, we are going to idealize the situation by considering an infinite solenoid. Okay, so that solenoid will be of infinite length. However, the result will apply quite well to, the magnetic field that we will find for an ideal solenoid, which is an infinitely long solenoid and it's densely packed. The result applies well to a very good approximation to a normal solenoid of finite length, given that we are near this axis of the solenoid, that's not off the axis, much off the axis, which are near the axis, and also away from the edges. Okay, so the expression that we will derive now using an ideal solenoid, that's an infinite solenoid, applies to a normal solenoid when we give the magnetic field of a normal solenoid near the axis or around the axis, not far from the axis, and away from the two edges or the ends of the solenoid. This figure shows how a cross-section of an ideal solenoid. This doesn't look like solenoid, but what I'm doing here is that if this is the solenoid, I am taking a longitudinal cross-section of the solenoid, okay, here, and I'm cutting it, and I'm looking at one of the halves, okay. So this is, for example, the part of this is one circle or one ring, one turn of the solenoid where the current is going. It should be coming this way, and the current is entering into the other ring, the page here, and completing the ring. But I have cut it half, so this is half a ring. The other half is inside the page. And so these are the ring stuff. So here in each one of them, the same current passes, because the same current passes through all the turns of the solenoid. And these lines showing me that this is an infinite. Now, the blue lines here show the magnetic field lines inside an ideal solenoid. As you can see here, well, almost, I have drawn them, they are equally spaced and they are parallel lines, indicating that the magnetic field is actually uniform. Now, why is the magnetic field uniform? This has nothing to do with Ampere's law. It's just due to the symmetry. How can I see that the magnetic field here is uniform? Well, one way of seeing it is just, let's remember what was the magnetic field of a single ring, current carrying ring, that we have worked out using the Biot-Savart law, and then we looked at how does it look. Well, here in the middle, it looks like, we have these lines here, but near the middle, it is almost uniform. Okay, and these lines, of course, here, they are coming from here, this is coming, and so on. So if the current is flowing in this direction, this is the north, and this is how it looks. Okay, so this is your ring, this is how the current is flowing, the direction of the arrows on the magnetic field lines will be in this way. So the magnetic field in this region looks like this. Now, when you bring infinitely many of those and stuff them on top of each other, then the superposition of the magnetic fields of each one of them will lead to a uniform magnetic field, because you will have, when you put on top and on the bottom, you will have some cancellations and you have some superposition. Okay, you have to just try to think of this with a bit details. It's hard to tell unless one really try to imagine that. So if you put another ring here, you will see that cancellation will take place among these, and enhancement will take place near the center of the or the axis of the ring. And so when you put infinitely many on top of each other, then this is the magnetic field that you will have. Outside, you will have zero magnetic field, because these here, the magnetic field lines inside, will cancel each other when you have rings on top and bottom. Okay, and this, because I'm talking about infinite, so you'll have infinitely many of these, and therefore we will have cancellation for outside, and also we will have enhancement inside, so that the magnetic field will be just uniform. So an ideal solenoid, which is infinitely long solenoid, will have a uniform magnetic field inside and zero magnetic field outside. Well, a real solenoid will of course have an almost uniform magnetic field in the middle near the axis, and a very weak magnetic field outside. Okay, very weak in comparison to this, because of the same reason, especially when you are away from the end. I'm talking when you are away from the end. Okay, so this is what happens. So this is the magnetic field that I have for an ideal solenoid. Now, my task is to find what is this magnetic field. I know its direction, and I want to find what is the magnitude of the magnetic field, and I want to apply by applying Ampere's law. Well, what was Ampere's law? It was B dot dl equals mu naught I net. Okay, so I need, first of all, and this was contour integral or a line integral, I want first to choose what is my contour. Now, I choose as a contour in this case a rectangle, okay? And this rectangle has a length L and has width W. And this rectangle, part of the rectangle is inside the solenoid, and the other half is outside the solenoid, okay? And it has four sides, 1, 2, 3, 4. 3 and 1 are parallel, 2 and 4 are also parallel to each other. Now, why a rectangle? It will be clear in a minute. Of course, this choice, now I am just saying, okay, this is what you chose. It's very easy. I'm showing it in 10 seconds maybe. But of course, choosing this for the first time, okay, in history was not that easy. I mean, it took people a lot of thought, trial and error, and so on, until they came up with this choice. But this is quite an ideal choice, as we will just see. Now, the arrow here shows the sense in which I am planning to traverse this magnetic field. This C. So this is my C. So I am traversing it clockwise, and this gives me the direction of dl. Now note that here on this part and in this part, the magnetic field is 0 for an ideal solenoid. Okay, so the magnetic field can be taken to be 0 outside in these regions. Okay, this is keeping this in mind. The magnetic field here, here, and here is not 0. However, this is a rectangle, and so it's perpendicular to the magnetic field lines. So if we want to choose DLs, let's see our DLs. Our DL here, because this is the sense of traversing the load, this is my DL. So DL here is parallel to B, okay? Where if you look at it here, for example, here this will be your DL. DL here is perpendicular to B, and also here this will be your DL. DL here is also perpendicular to B, so keep this in mind. And the magnetic field outside is 0. So there's no magnetic field here, there is no magnetic field here, there is no magnetic field here. Okay, so this is, let's just keep this in mind. Okay, now I want to, and what is the current in the enclosed by this loop, because I want to know what's the right hand side. Well, it is the sum of the number of turns multiplied by I, because each of these crosses here resembles a turn, one of these turns, and each one of them carry a current I. So it's actually how many of these you have here multiplied by the current flowing in the solenoid. Okay? So let me move to apply Ampere's law. Now we will see that this is a very convenient contour actually. We start by noting that this integral over this closed contour can be decomposed into integrals, line integrals. This integral b dot dl integrated is called the line integral, as I have just said, into line integrals over 4 open paths, contours, not closed contours. So this reduces to integral over b dot dl, for example. I start from here, 4 plus integral over 3 b dot dl plus integral over 2 b dot dl plus integral over 1 b dot dl. Okay? So this left-hand side reduces to this, as you can see, because when you add up, when you integrate over these 4, you are integrating over the whole closed contour that you have picked up. Okay, so let me start with 1, for example, or let me start with 2. Now along 2, the magnetic field is equal to 0. B along 2 here is equal to 0. So the whole term here is 0 because 0 times dl you are integrating is 0, so it's just 0. So the integral here is 0. Now let me look at 3 and 2, which actually, and 1 and 3. They are similar actually. So let's consider 3, for example. Now 3 is composed of 2 parts actually. One part outside the solenoid, the other part is inside the solenoid. For the part that is outside the solenoid, the magnetic field is 0. So for this part of 3, which is outside the solenoid, also the integral is 0. Now for the part which is inside the solenoid, the magnetic field is not 0 on this part, because there is a uniform magnetic field. It is inside the solenoid. However, as we have seen, because this is a rectangle and I have chosen it so that this upper and lower sides are perpendicular to the magnetic field, then the angle between dl and b all over this part is always pi over 2. So cosine pi over 2 is 0. So the dot product b dot dl within this part is 0. So within this part of 3, the integral also is 0, but not because b is 0, but because b is perpendicular to dl to dl over the whole part. So therefore, this is also 0. Exactly the same argument applies to side 1 here, and this is also 0. So this boils down to just integral over 4, the fourth contour, okay, which is this side. Now here, of course, life is very easy because the field is uniform by definition from the symmetry, magnetic field. dl, I have chosen it this way. It is, and this side is parallel to the field lines, and so the angle between b and dl is all the way 0. So b dot dl is just b. B is constant. You take it outside, so it reduces actually to b dl. This is the left-hand side. What about the right-hand side? Mu 0 multiplied by I net. Now, I net is the current that is flowing inside the area bound by the curve. And as I have said, it's the number of turns multiplied by the current flowing in the solenoid. If the current flowing in the solenoid is I, and we have n of these, so this is general, I want to make it general. So you have n multiplied by I. N is the number of turns within the area bound by the contour C. Now, there's one thing. Is this positive or negative? I have to check. Okay? My right-hand rule. How I have traversed the contour? I have traversed the contour in this direction. So I let my right-hand fingers curl in this direction. My thumb now is pointing into the page. Where is the current pointing? It's into the page. Good. So it's positive. So Ni. There is no minus Ni. Okay? And therefore, I have this expression here, b integral over dl equals mu Ni. But what is integral over dl? It is the length of this side. So I get b L is equal mu naught Ni. So now take L to the other side. So b is equal mu naught N over Li. Now, N over L is the number of turns within L divided by the by the length. What is this? It's the number of turns per meter, which is the density, actually, of the turns. And how many turns you have per unit length. So call this small n. So this becomes B is equal mu naught n I. So B inside an ideal solenoid is given as a uniform, as we have seen. It's just mu naught multiplied by the density of turns, which is n, how many turns per unit length, multiplied by the current. So if you want to enhance the magnetic field in a solenoid, you just pack it more densely. This is why probably you see in applications the solenoids are more always densely packed, or increase the current in it, or both. Okay, or both. So this is how you can increase the magnetic field inside the solenoid. As I said, this result we have derived it for an ideal solenoid, but it is valid for a normal solenoid near the axis, not much off the axis, okay, and away from the side, the edges.